Good day, everyone. Today we shall be considering circular motion. And under this study, the following shall be considered: 1. Motion of cars on banked road. 2. Example involving cars on banked road. And then exercises on cars on banked road.
Next, on this same circular motion, we want to look at cars on a banked road. Now, under this, I want to explain that there are some roads that have what we call kind of sharp turning. Maybe you have to turn in this manner on the road. The turning is a very sharp one. And the roads, if they are built horizontal, maybe the express road looks like this, or the road looks like this, and they are going to turn in a manner like this, most often the cars tend to skid while you are making this sharp turning. And the reason is because the road is just looking horizontal. Now, during construction, it's important to bank this road. That's why some road, you realize that they are actually built in this manner, kind of a little bit tilted, and cars move on it, kind of like this. In this case, you say the road is banked because it is in this manner. And so what we want to see is the force acting on a banked road, or at what banking angle should this be built so that sufficiently you can do this turning without a car skidding. You see the back tires skidding out of the road path, and that's because probably the road is not banked, and friction is not enough to keep that object moving in that circular manner. Well, let's look at this now. If I have a road like this and probably banked, I will have a road that should look horizontal before. It's now in this manner. Cars are riding on it and the road is like this. The angle here is called our banking angle. Let me assume I have a car. Please don't mind my diagram now. So cars on this now. So moving like this on the road. Now the next thing we want to bring out here is that the forces acting on this car. First of all, I will have the weight acting vertically downward. Then I will have the reaction acting in this manner. Now, this is our angle here. This angle theta here will be see the same angle here, theta. Now, the next now is what other force can be acting on this? Well, understand that this reaction here contributes what we call the centripetal force, the force that acts inward here. And since we have centripetal force, we also have what we call centrifugal. mv squared over r. Now, as a result of this interaction, we want to ensure that the object is kept in equilibrium, that it does not skid. And if that should happen, let's look at what our banking angle should be, or what the tension that we're acting on this object, or the force acting on this object. So briefly now, I want to say, if we resolve this reaction now vertically, let me draw a vertical line upward here. And the angle here will be also theta, because this is vertically opposite to this. So if I resolve vertically, I will have r cos theta is equal to the weight of this object. And we can say r cos theta is equal to mg, because weight is mg. Again, if we resolve horizontally now, or along parallel to the plane, that's the best word, that's the right word to use. Parallel to the plane. This is equation 1. We would have r sine theta. And that will be equal to mv squared over r. Actually, how did I even get this? I think I jumped steps here. So let me explain. So at the end of the day, I said R cos theta, then minus W. R cos theta, that's when it is up here, pointing upward, and then the weight is already acting downward already, is equal to, at the end of the day, it's not, the body will not accelerate because it's at equilibrium, equal to 0. And that's how we got this. So, and then again, if you resolve this parallel to the plane, that will be R sine theta. Then plus, so this is negative, because pointing like negative x direction, and then plus mv square over r. After these two interacted, it is not accelerating because it's at equilibrium, equal to 0. And that will give us the second equation. This becomes my equation 2. So that's how we got this actually. Now, with this, now I can say divide equation 2 by 1. Equation 1. So that will be r sine theta, equation 2 now, is equal to mv square over r divided by equation 1, r sine theta, divided by mg. Eventually, we have r cancelling r. So this is cos, not sine, cos. I'll be left with sine theta over cos theta being equal to m, eliminating m here. And this r comes down with v square over rg. Sine theta over cos theta will give us tan theta. So tan theta is equal to v square over rg. Bringing these two here, and this over 1, cos multiplying v square times 1 will give me v square. And that's equal to rg tan theta. And then we can tell that v is simply square root of rg tan theta. So this is the velocity for the object moving on a bank, or the maximum velocity it will have before it can skid, or the velocity that keeps it at equilibrium. So that's that about that. And we can use this also. It is the maximum velocity it should have. This should be the banking angle. This is theta, the banking angle. So that's that about this. Number 1, a car is racing on a circular track of 180-meter radius. We are giving the radius as 180 meter, and banking angle theta as 30 degree. Let's take our G now as, let's say 10, or you can say 9.81. Okay, so what's the speed? What should be the speed of the car? This is simply saying the maximum velocity you should have for the car not to skid. Any velocity less than the maximum, the car will not skid. But if you see the maximum, the car could still skid. So this will be, to get the velocity, we have that here now. Velocity is equal to rg tan theta, all into square root. So our radius is 180 times the g, 10 times tan 30, all into square root. So that's that for this question. Let's evaluate that now. Square root of 180 times 10 times tan 30, 32.24 meter per second. So that's the maximum velocity one should drive on this road. So that's that about that. Okay, so this is an exercise for a banking angle question where the road is banked. So, and that is the answer.